Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. In 1929, astronomer Edwin Hubble discovered that the universe appears to be expanding. This changed our fundamental view of an eternal and constant cosmos. We found that our universe is caught in a cosmic struggle of expansion versus gravity. We can see that on the largest scales, countless galaxies are moving away from us and each other. If this continues forever, creating what is known as an open universe, the sky will one day be hopelessly cold and dark. However, if gravity has its way, as some believe it inevitably does, the galaxies will eventually fall back in on themselves, closing the universe in crushing density and infinite heat.
That's the comparison, the choice that Harlow Shapley gave to Robert Frost, who wrote a poem, that some say the universe will end in fire and some say ice. Human nature being what it is, we have a stake, we feel, in the fate of the universe.
Present-day scientists peer down unknown paths as they try to divine the nature of the universe and its ultimate fate. Their quest begins close to home, with galaxies like our Milky Way.
It had always been assumed that in a spiral galaxy, as you went further and further from the dense central core of the galaxy, that the stars would be moving slower and slower. Just as in the solar system, the outer planets move slower and slower because of their distances from the sun. What we see in virtually every case is that the velocities of stars far from the center of the galaxy remain high.
We infer from that that the gravity field of the Milky Way and other spiral galaxies is not concentrated where the light is, where the stars are, but is spread out much more diffusely. When you do the arithmetic, you find that 90% of the mass of the Milky Way galaxy is dark, it's invisible, it's helping to pull the stars around in their orbits.
The idea that there was matter in the universe that no one could see originated early in the mid-30s, principally due to the work of Fritz Zwicky, a Swiss astronomer. He noticed that in clusters of galaxies, the individual galaxies are moving very rapidly with respect to each other. And he therefore concluded that there must be material in the cluster that he could not see that was holding the cluster together, or otherwise the galaxies would just disperse. And he realized that that wasn't happening. And Zwicky called this missing matter. When the studies of individual galaxies in the late 70s, early 80s that I was doing and other people were doing showed that individual galaxies also had properties that made us realize there was matter that we didn't see. The only thing we didn't like was the name that Zwicky had used. He had called it missing matter, and we understood that it wasn't the matter that was missing, it was the light that was missing. The matter is there. And so, as a body, we just started calling this dark matter.
Perhaps not surprisingly, an earlier theory by Albert Einstein foresaw one of the most startling pieces of evidence for the existence of dark matter.
One of the predictions of Einstein's theory of relativity is that light waves are bent by gravitational fields. Now this means, and it was recognized by Einstein very early, that the gravitational field of a star, or as it turns out a galaxy or a cluster of galaxies, will bend light and can act as a lens. Now the lens has a number of properties, one of which is that it makes background objects appear either brighter or dimmer than they otherwise would. And in the case of gravitational lenses, typically one produces multiple images of a background object. So we frequently see 2 or 4 images of background objects. The gravitational lens itself is actually the gravitational field of the object. We infer the amount of mass needed to produce that gravitational field. Now, this amount of mass turns out in all cases to be much larger than the amount of visible material seen in stars. So this is evidence that there's a lot of dark matter in these objects.
If we attempt to image this dark matter, if we take very deep photographic plates, or if we look at 21 centimeter hydrogen, or any wavelength that we can observe in, we don't see anything. So whatever this matter is, our belief at the present time is that we have been unable to detect it at any frequency. And so it is either very, very faint, or it is in fact not radiating at all.
On an emotional level, it's a little embarrassing to suddenly discover that we've been neglecting most of the matter in the universe, that several centuries of astronomical study have been studying the minority trace constituent of the universe instead of the majority, which is the dark matter.
There are enormous numbers of possibilities for the dark matter. It could be anything that does not obscure the light from something behind it, so it has to be in fairly small pieces. The problem is that if it's a very small thing, then we need enormous quantities of it. The rotation curves indicate that perhaps 90% of a galaxy consists of dark matter.
So we all agree that there is a very large amount of the stuff of the universe that we don't see. Is it 90% or 99%? We don't know yet. And depending on this number, we could have two different possibilities for this dark matter. If it's only 90% of the stuff in the universe, we can, at the limit, believe that it is ordinary stuff, what we call baryonic dark matter.
Baryons simply mean ordinary matter, particles of which we're made, protons, whatever. How could this stuff be dark? Well, for example, a star, like the sun, eventually turns into a white dwarf. Other stars may become black holes. Those are perfectly good examples, eventually, when all light's faded away, of dark objects, or planets, another type of object which could be very dark. The universe could in principle be full of stellar remnants or planetary-like objects. We refer to that as baryonic dark matter. However, that's only one possibility.
One finds, and this is quite fundamental, that it's not possible to have enough baryonic material in the universe to do what we call close the universe, or make up a critical density of material in the universe. Now, there's theoretical reason to believe that the universe is in fact critical in the sense I described. If that's the case, then there's a lot of non-baryonic or exotic dark matter in the universe.
What can it be? Well, there are various options. One option is to say, what if these little particles called neutrinos that go whizzing through us and don't interact very much, but there are huge numbers of them. What if each little neutrino has a little tiny mass, not a very big mass, much, much smaller than the mass of the electron. But because we have difficulty detecting neutrinos, they're whizzing through us all the time, we weren't able to detect that they had this little tiny mass. If we give them this very little tiny mass, because there are so many neutrinos, then neutrinos would in fact be the dominant matter of the universe.
Neutrinos, gravitinos, axions, they call them WIMPs, generically, weakly interacting massive particles. If these particles exist, and if you can give them the right properties, so that they clump around galaxies, so that they don't disturb our ideas about how galaxies formed from the initial perturbations and how long it took galaxies to form, then the universe could consist of this dominant fraction that we really don't know at the present time. There are lots of laboratory experiments underway to try and detect these particles.
We're in Bernard Sadilay's cryogenic lab, and we're trying to put together an experiment to detect dark matter, WIMP dark matter. The fridge is over here. The cooling is done by these, carried by these set of nested tubes. There's one tube on each of the cold stages of the fridge, and they go over to a set of nested cans. This is the outermost can that, again, are connected to the various cold stages of the fridge. The innermost of these, there's 5 altogether. The smallest one is about 1 foot in diameter and 1 foot high, and that's where the detectors go. And at that point, the detectors are cooled to 10 millikelvin.
Okay, what we have here is E2, and E2 is a 60-gram crystal of high-purity germanium, and we use it to actually detect the phonons, which are the sound waves or the heat produced in a crystal when an incident particle strikes and recoils off of a nucleus or an electron within the crystal. It has on it 6 NTD germanium, neutron transmutation doped germanium thermistors. Similar detectors will be used in a low-temperature dark matter search experiment.
With experiments such as these, scientists may be closer to uncovering the secrets of dark matter, but the elusive substance remains a mystery.
Not everybody believes in dark matter. There is a very small minority of cosmologists who believe that we've got the theory of gravity wrong. That in fact, the reason we're measuring this extra pull on larger scales is simply because Einstein's theory of gravity is breaking down. There's no evidence for that whatsoever. We've measured systems where the gravity field is very, very strong, such as the binary pulsar, where there are 2 neutron stars orbiting around each other, which are a great test of gravity theory. Everything seems to work as far as we can tell, but nevertheless, it's very hard to prove that on large scales of millions of parsecs or hundreds of thousands of parsecs, there could be flaws in our understanding of gravity.
We may be seeing the emergence of a second Copernican revolution, or maybe the ultimate Copernican revolution. Since Copernicus, we know that we are not at the center of the universe. But if it's true that 99% of the stuff in the universe is not made of ordinary matter, we are not even made of the stuff the universe is made of.
The presence of this dark matter could also influence the ultimate fate of the universe. Today, the universe is expanding. We see every galaxy moving away from every other galaxy. The dark matter might contain enough mass to exert enough gravitational tug to eventually break the expansion of galaxies and reverse it into a contraction, so that some very long time from now, instead of seeing an expanding universe, we could have a collapsing universe, due largely to the presence of this dark matter.
As strange as dark matter seems, even stranger may be its role in the fate of the universe. For it's the amount of matter in the universe and its rate of expansion that provide our best clues to the future.
Shortly before Hubble's law was identified, in 1917, Einstein published his theory of relativity, the general theory of relativity, in fact, which depends on the presence of matter in the universe. Once you postulate that there's matter in the universe, and I think we have good evidence that that's true, then you postulate the existence of gravity. The effect of gravity is to cause all objects to be pulled together. And so Einstein found that in order to prevent his universe from collapsing, he then postulated another kind of a constant called the cosmological constant, which prevented this collapse. The cosmological constant represented a repulsive force to counteract gravity.
When the Hubble expansion was discovered, Einstein then, in fact, dropped the cosmological constant and said it was the biggest mistake of his life. But he had sort of let the cat out of the bag, and people have continued to talk about this as a possible component of the cosmological expansion. That component could be used to adjust the difference between the observed expansion and the ages that people see, and that's frequently cited as a possible explanation.
The rate at which galaxies are expanding away from each other is known as the Hubble constant. Once that exact rate is known, we will be better able to determine both the age of the universe and its probable destiny.
It's like deciding how long it takes to travel from Los Angeles to San Francisco. If you know the distance between the two cities and you know how fast you're going, then you know how long it will take you to get there. In exactly the same way, we see two galaxies. We know, having measured the distances, how far apart they are. We can see the velocity of this galaxy, so therefore we know how long it took that galaxy and ours to separate that distance.
If you know the rate at which the universe is expanding, you can invert that process in your mind and run the film backwards, then you can predict how long ago the Big Bang occurred.
The present uncertainty in Hubble's constant by a factor of 2 means that we're always arguing with one another over the age of the universe. Is it 10 billion years? Is it 20 billion years? Nobody knows, and this is a major uncertainty.
Right now, we don't know which group is right, whether the people who get long ages from the Hubble dynamics or the people that get short ages. It is interesting that the ones who get the long ages are consistent with everybody else, and there's no problem, no conflict. On the other hand, if eventually the people who get the short ages win, and they show that their technique is indeed the right one, then there would be a conflict. Then we would have to come up with some explanation of why the dynamical technique, the Hubble technique, is not giving us a good estimate of the age of the universe itself, but is measuring something different.
One of the major goals of the Hubble Space Telescope is to measure the scale of the universe and thus Hubble's constant. The core of this is getting distances to the nearest galaxies. Fortunately, there is a kind of star called a Cepheid variable, which seems to be very uniform from place to place. It's as though these things were stamped out with cookie cutters.
The Hubble telescope allows us to see them to a much greater distance in galaxies that are far enough away to participate in the general expansion of the universe. And it's really, I think, quite probable that in the next 5 years, the distances to those galaxies will be gotten in a more direct way than they ever have, and then we'll know what the Hubble constant, the expansion rate of the universe, actually is.
This is like creating your own ruler for the size of the universe. Once we know distances in the local area, we'll be able to extend that scale out to the edge of the observable universe.
One way to determine what the fate of the universe is to measure the Hubble constant in the past by looking very far away and compare it with the rate now and see how rapidly the universe is slowing down, whether it's applying the brakes, so to speak, fast enough that it will stop, or whether it'll just escape the pull of gravity and expand forever.
Two roads diverged in a yellow wood, and sorry I could not travel both and be one traveler. Long I stood and looked down one as far as I could to where it bent in the undergrowth.
We really don't know at the moment whether the universe is open or whether it's closed. And the distinguishing characteristic that we need to nail down is the density of the universe. So as we struggle to find all of the matter in the universe and inventory the universe and determine its average density, we're really trying to find out whether it's open or closed.
Einstein's great contribution in general relativity was to link gravity to the curvature of space. In the expanding universe, the space of the universe is curved. This represents the fact that the universe contains matter. A universe with more gravity, which is one that will expand and eventually have enough gravity to recollapse, that universe has stronger curvature.
Some astronomers have referred to this point in time when the universe stops expanding and collapses back on itself. All the material will come back to where it started. Some people have called this the Big Crunch. Whether that will happen or not depends on the amount of matter in the universe.
If the density of the universe is high enough that the gravitational attraction can cause the expansion to slow down and eventually to stop and reverse itself, then the structure of the universe must be a spherical structure like the structure of the surface of the balloon. We call this a closed universe because the universe, in terms of the surface which it represents, is a closed surface.
If gravity is able to overcome the expansion of the universe that we see today, such that it stops the expansion and then things begin to fall back together, then all of the matter and all the energy and all of space will be collapsed back into a very high density, high energy state like the Big Bang.
A more complicated geometry of the universe is represented by the case in which the gravity or the density of the universe is not great enough to stop the expansion. In this case, the universe is a so-called open universe or hyperbolic universe, often called saddle-shaped and represented by the surface of a potato chip. In this case, the universe will continue will be infinite in size, continue in both directions infinitely.
If the universe is open, by which we mean that galaxies will rush away so rapidly that the force of gravity that tends to retard them is overwhelmed and they will expand away from each other forever, then the consequence of this is that the universe will just grow colder and will run out of nuclear energy sources of the energy sources of stars. It will grow dark and cold. There might be sort of pockets of high energy zones that have defeated this process, but in general the universe will be cold and dark.
The question of whether the universe is open or closed is really just a question of, is the density of the universe greater than or less than the critical density? An open universe is one that expands forever to the big chill. A closed universe is one that falls back in on itself to the big crunch. If you're right at the boundary, it turns out to keep expanding forever, but just marginally so.
Given these two choices of being open or closed, it's clear that it's remarkably close to the boundary between the two things. The universe could be so open that it would have expanded in microseconds or seconds. It could have been so closed that it would have collapsed, expanded and collapsed in the same very short time. But in fact, it's been going for billions of years and seems to be a rough equivalent of gravitational energy and the energy of expansion. So we know it's close to the boundary. This in itself causes some people to speculate that it must be exactly balanced, because it would be too big a coincidence to be close to balance but not be exactly to balanced.
Big Bang nucleosynthesis tells us that the density of ordinary matter is only 10% of the critical value, and thus it's an open, ever-expanding universe if we only have ordinary matter in it. On the other hand, there's some evidence from the large-scale motion of objects in the universe that seem to imply that the actual density of matter in the universe is somewhat bigger than 10%, in fact, probably approaching the critical value. The fact that we're here talking about things now tells us that the universe is not at infinite density nor at zero density. The only other answer that can be a long-lived answer is that the universe is very close to the critical density.
Now, why is space-time flat? One possibility is because the universe went through an inflationary epoch in which it got vastly larger than we had thought. In that case, the observable universe would be only a tiny part on this enormous balloon of the potentially observable universe.
This is a theory due in its original form to Alan Guth at MIT. And this theory holds that there's a period in the universe where it suddenly expands incredibly rapidly, and that's why it's called inflation. The universe is inflating very many times over, grows much larger. And this rapid expansion stretches the space-time flat, as it were, and then comes to an end by processes that are still not very well understood.
Inflation occurred when symmetry of the universe broke. Imagine taking a pencil, okay, standing on a flat surface, pointed, sharp pencil. It will fall down in a random direction. Clearly, when it's fallen down, the symmetry is broken. It's pointing to some direction. When it's vertical, things are perfectly symmetric. Okay, so there was some change in the universe, which you can think of loosely perhaps as being at one time there was equal amounts of matter and antimatter, and as the temperature dropped, everything annihilated and only the bits of matter were left behind. This change has the effect of releasing energy. That release of energy is the explanation of why the universe went through a sudden, brief burst of acceleration, which we call inflation.
The inflationary theory has the problem that it's highly speculative and very difficult to test directly. But it has the virtue that it's very simple and very elegant, and it makes a very precise prediction for the state of the present universe. It predicts that the amount of material in the present-day universe is almost exactly critical.
If that's the case, space-time is so nearly flat that we may never be able to tell whether the vast universe is open or closed, because it'll just be too big. It's possible that every observer in the universe is in this conundrum, that if it's an inflationary universe, that they never really know what the fate of the universe is going to be. But it becomes almost irrelevant because of the sheer dimension and wealth that the universe contains within it.
So the future of the universe may have been sealed in its first second, when matter crystallized from a hot inflationary Big Bang. As we discover more about matter and gravity, we move closer to learning the fate of the universe.
An important thing to take away from any study of cosmology is that there's so much more not known than known. On the observational front, there's an enormous amount to be learned. We don't know what the dark matter is made out of. That has to be the most pressing issue, I think, for cosmology, and to try and figure out what makes up 90% or more of the universe. And on the theoretical front, there's a lot of work going on still on the inflationary theories, because the theories are not complete. They're very compelling and very attractive, but they haven't been fully worked out.
One of the tantalizing prospects raised by the inflationary hypothesis is the possibility that our universe began as a bubble, just a bubble in the space-time foam of another preceding universe, and that preceding universe continues, and that many other universes, perhaps an infinite number of them, may exist sprouting off from one another, something the way that fresh new twigs sprout off from the branches of trees. Oddly enough, the laws of physics seem to permit this. If so, it's possible that in our own universe, unknown and unbidden, from time to time, a quantum flux, random flux somewhere in space, gives birth to another universe.
And both that morning equally lay in leaves no step had trodden black. Oh, I kept the first for another day, yet knowing how way leads on to way, I doubted if I should ever come back.